Now we go ahead with the next topic, which is called as layout design rules. So now we are now familiar of what exactly is fabrication, and after you fabricate you have the device, and along with that we have understood how to do the logic gates, how to represent the schematic of NAND gate, and that in turn we have also shown the other version of doing or converting the schematic into a stick diagram, and from the stick diagram we are able to convert it into a layout diagram. So now I think you have the virtual view of how exactly a layout looks. So you have horizontal lines, parallel lines, vertical lines, slanting lines. They all represent the layers used in MOS structure. So what should be the rules for these layers? That is called as layout design rules. So layout design rules describe how small features can be, and in industry design rules are usually specified in microns. So you can't have your own thickness of these lines randomly. You have to follow some industry standards, and normally the industry standards are in terms of microns. So whatever the dimensions you are doing, it should normally be in terms of micron, either 1 micrometer or zero point 0.1 micrometer or 0.01 micrometer. That is how we are able to achieve the smaller version of the design. 0.01 micrometer is in other words nothing but 1 nanometer. So we will be using a parameter called as lambda. This lambda is equal to one value. In earlier days, when we were understanding lambda, lambda was equal to 1 micrometer. But now the lambda value has shrunk, it has been made small, it is equal to 0.09 micrometer. So reduction of 0.01 is a major achievement. So that is the new value assigned for lambda, and from this itself we go ahead. The length is the distance between the source and the drain of a transistor is set by minimum width of the polysilicon wire. This is nothing but your channel. So the channel width is set by the polysilicon wire. Why? Because polysilicon, when it is overlapping with the diffusion, a transistor is created. That itself is called as a feature. And for 180 nanometer, we have the minimum polysilicon width. So the minimum polysilicon width should be of 0.18 micrometer. And as per the design rules, lambda value is equal to 0.09. So 0.09 into 2 will turn out to be 0.18 micrometer. 2 lambda. 2 lambda is the size of the polysilicon. So the design rules are considered in terms of lambda itself. So lambda is a globally accepted variable which helps us to keep in mind in order to design the feature. So designers often describe a process by its feature size, and it refers to the minimum transistor. Next we have something called as MOSIS rule. It is metal oxide semiconductor implementation standard, MOSIS. These are also expressed in lambda. MOSIS service is a low-cost prototyping service that modifies designs. So using this, we are going to modify the design. It is a tool. This rules between the minimum width. What is the purpose of rules to be followed? You should have minimum width in order to avoid the breaks in the line. There shouldn't be overlappings. There shouldn't be shorts between the lines. Whatever is there, you ensure that they are clean and neat and separate. Equivalently, you should have adequate spacing in between. So it is easy to follow this design rules with two metal layers. As I have told you, you will be considering two metals, M1 and M2. So M1 is meant for inputs and outputs, M2 is meant for VDD and VSS lines. So minimum dimension of metal and diffusion is of 4 lambda. So whether it is M1 or M2, both will be using 4 lambda thick. Diffusion also is of 4 lambda. So metal and diffusion is of 4 lambda. Contacts are of 2 lambda. So in case you have any extra contacts, that should be scraped out. Contacts are of 2 lambda cross 2 lambda because it forms a square, and on either side length and breadth is considered, it forms 2 lambda cross 2 lambda. And on either side you should have 1 lambda. It is surrounded by 1 lambda on the layers above and below. And the polysilicon thickness, that is also 2 lambda. Whenever you have polysilicon overlapping the diffusion, transistor is formed. And when you have the transistor, the spacing should be of 1 lambda where no transistor is desired. In case you have another transistor, you should give a spacing of 1 lambda. Polysilicon and contacts have a spacing of 3 lambda. The distance between polysilicon and contact should be of 3 lambda from other polysilicon or contacts. N-well surrounds PMOS transistors by 6 lambda and avoids NMOS transistors by 6 lambda. In the next diagram you see, you will understand much better of what I am talking. As I say, this is one contact, you have another contact. So the spacing is between the well. From here to the well, the distance is 6 lambda. From here to the well, it is 6 lambda. So totally you have 12 lambda. The last statement what I told. And similarly, this is your, whatever is indicated in blue color is your metal line. And this is one which is indicated in black is your polysilicon line. And this gray color shaded region is your N-well. So transistor diamonds are often measured by W by L ratio. So W indicates the width, L indicates the length. We have W by L as 4 by 2. Therefore, it has a feature size of 2 is to 1. How is it possible to construct this kind of transistor? So width, normally the width is the diffusion. So the diffusion is of 4 lambda. Polysilicon is the horizontal version, which is 2 lambda. So whenever you have a diffusion of 4 lambda and a polysilicon of 2 lambda, this is the dimension of the transistor being created. And normally PMOS transistors, the width is more because in PMOS the holes are the charge carriers and they are very slow compared to the mobility of electrons. So once the width is big, wide enough, more electrons, more holes can flow, and as a result, the mobility of holes are comparatively made little better than the earlier flow. So this is based on the design rules, metal 1 and metal 2 both of 4 lambda, and the spacing between them is also 4 lambda. This is metal 2, here this is the representation, this is one line hatching, here you have a cross hatching, so this is 4 lambda. And if you just see the top view, this is how the metal 1 to diffusion contact. You have this as a contact. This is the contact established between metal 1 and diffusion. This is the contact established between metal 1, polysilicon and metal 1 and polysilicon. This is vias between two different metals you have. This is the distance which is called as vias. So this is a unit inverter layout with a unit NMOS transistor and a double sized PMOS transistor. As I told you, N is of 1 dimension, P is of 2 dimension. So how do we get this kind of a structure? So you look into this figure B. This is how W by L ratio is considered. So you have the PMOS transistor on the top, 8 by 2 is 4, and in the bottom 4 by 2, which is NMOS, is 2. So 4 by 2, when you divide on either side the ratio, PMOS and NMOS, you will get the value of 2, and that is what has been shown here, 2 is to 1. So this is how we need to construct. Keeping this in mind, we need to construct. So in order to get 2, it is nothing but W by L. So your W should be 2 and L should be 1. Therefore, W minimum width of the polysilicon of the diffusion is 4 lambda. So less than 4 you can't use. So you have to use the diffusion of 4 lambda and you have to overlap it with the polysilicon of 2 lambda. So 4 by 2 will reduce to 2. This is how it is being constructed. This is how the layout looks like. So you have diffusion of 4 lambda and you have polysilicon of 2 lambda, and that is how this transistor is created inside the well structure. Next, the same version has been assumed with unit width. We now have a discussion on gate layouts. So we have two figures here. Figure A shows the layout for an inverter. So we have already been familiar of how to demonstrate the layout representation. So you have P diffusion in the pull-up region N diffusion in the pull down region, and you have vertically the polysilicon. So a transistor is created. So this is the transistor. Polysilicon is nothing but your input. So this is your input A, and if you notice the two drains are shorted. This is where you have Y. The source of PMOS is connected to VDD. The source of NMOS is connected to ground. So this is the layout representation of an inverter. And similarly, figure B shows the same inverter with well and substrate taps. And okay, one more thing I wanted to tell you. So this is the well structure, light gray color. Same thing, even this is your inverter layout itself, but we have something called as well and substrate taps. So what exactly you mean by well and substrate taps? That well is coming inside and there is a tapping taken over here. Similarly in the substrate. So you have a strong connection, strong contact between the well, which is normally connected to VDD, and the substrate which is connected to the source, and it is grounded. Same grounds, we now have a figure of 3 input NAND gate. So the 3 input NAND gate is shown. This is your VDD and this is your ground, and 3 input. So 3 inputs. So the 3 inputs are A, B and C. And when you notice, all the 3 inputs are connected in series. Source, drain, source, drain, source, drain. And this is where we finally take the output. So NMOS transistors are connected in series, as I already told, while the PMOS are connected in parallel. And these are the examples which use the transistors of width 4 lambda. That means the diffusion. The diffusion is of 4 lambda, and the metal lines are also of 4 lambda. So next we have a demonstration of something which we need to understand, called as pitch of routing tracks. It is easy to estimate the area of a layout. So once you have the layout, you are supposed to find out what is the area occupied by that particular layout with respect to the stick diagram, or with respect to the layout representation. So how do we find out how much is the area occupied by the layout? If our wires have width of 4 lambda and a spacing of 4 lambda to the next wire, that means you have one wire. Normally I have told you the width of the thickness of the wire is 4 lambda, and you have another wire which is also of 4 lambda. The spacing between them should be 4 lambda. So 4 plus 4 plus 4, totally there will be like this. This is 4 lambda and the difference is 4 lambda, and last one is 4 lambda. So 4 plus 4 plus 4 inclusive of the third metal, the second metal is becoming 12 lambda, but we are not considering the second lambda. The pitch is the difference. So the difference here is called as 4 lambda. You simply can't take it as 4 lambda. You have to consider the first metal. Therefore we call that as the track pitch. So when it is 4 lambda and the difference is 4 lambda, it together makes 8 lambda. So which is shown here also as well. 4 lambda and 4 lambda, this is how you have 8 lambda. The pitch also leaves room for a transistor to be placed between the wires. Figure B. So there is also possible in between this space you can have your polysilicon, or you can have a transistor being created. Therefore, it is reasonable to estimate the height and width of the cell by counting the number of metal tracks and multiplying by 8 lambda. So simple to understand. Whenever you are having, we'll see that later on, whenever you are having any metal to metal area you need to calculate, you have to mandatorily multiply it by 8 lambda. Because we have now found out the pitch to be 4 lambda of the metal, and the difference between two layers is 4 lambda. Together it makes 8 lambda. Now we'll find out that. Figure shows how to count tracks to estimate the size of 3 input NAND gate. So as I've told you, we are supposed to find out what is the area of this 3 input NAND gate. And 3 input NAND gate means 1, 2, 3. A, B, C. So these are the 3 inputs which are represented with the polyline. And also you can see there are 4 vertical wire tracks. Extended wire tracks. If you notice, this is one. Let me show you by drawing. This is 1, this is 2 metal track, this is 3, and this is 4. So you have 4 vertical wire tracks, and when it is wire you have to multiply it by 8 lambda. So therefore this is nothing but 4 into 8 lambda, which happens to be 32 lambda. This is where you have. So the width is given as 32 lambda. Width is 32 lambda. So horizontally we are supposed to find out now. Vertically we found, which is 32 lambda. There are also 5 horizontal tracks of the metal. So this becomes, well, let me show in a different color. 1. This is also the diffusion, which is shown here as 2. One, 2, 3. Here 4. This is 5. So you have to multiply it by 8 lambda. Again this turns out to be 40 lambda. So this is how we are estimating the area. So now you have 40 lambda and 32 lambda length and width. You multiply them both, 40 lambda into 32 lambda into lambda square. That becomes the area. Similarly in this diagram you can check 1. This is one line. 1. This is second line. This is third line. This is 4. And this is 5. So 5 tracks into 8 lambda, which is equal to 40 lambda. Next, vertically, how many you find? 1. Oh, okay, horizontally, sorry. 1 here, 2, this one, 3, this one, 4, 5 and 6. So 6 into 8 lambda, which happens to be 48 lambda. Multiply 48 lambda and 40 lambda, turns out to be the area. Now we will have a discussion on well rules. The well has to be quite deep enough so that it is clear, and end well edges as well as the end diffusions dimensions should also be provided. Once the well is quite deep enough, you will be able to place the NMOS or PMOS transistors so that there is no overlap and it is quite having sufficient edges space. So between the N well sheet resistance can be several kilo ohms. So the sheet resistance of the well can be in the range of bigger kilo ohms. Normally it is 10K, it can be more than 10K per square. Therefore it is necessary to ground the well. How do we ground the well? For the only reason why are we grounding the well is only for the because of the reason that it is high resistance. So that is the reason most of the time the well structure is connected to VDD. This will prevent excessive voltage drops due to the well currents. So since resistance is high, there will be abrupt resistance is high and current flow is less, and that shouldn't create any drops. Therefore, it has to be well connected. Next we have transistor load. CMOS transistors are generally defined by 4 physical masks: N-select mask, P-select mask, polysilicon mask. So the active mask defines area where N or P diffusion is to be placed, or the gates or transistors are to be placed. So what exactly you mean by active mask? It is the mask where N or P type diffusion is placed or the gates are placed. So only in the active mask P or N or poly is done. Diffusion is done. N diffusion areas inside the P well regions define NMOS transistors. Very much fine. In the P well, you have to have diffusions of N type. That is how you have NPN transistors. And similarly, N diffusion areas inside the N well regions define N well contacts. So and vice versa. So poly has to be extended, and this is often called as gate extension. Next we have contact rules. So how should we show the contacts? Contacts has to be established between diffusions, between polysilicon, between metals and between substrate. So these are the places where the contacts are established with respective to metal. There is another type of contact which is called as buried polysilicon active contacts. This helps us to have the local interconnect. Therefore, each isolated well must be tied to supply voltage. N well must be tied to VDD or substrate, and substrate or P well is connected to ground. This is only in the case of contact rules. So these are the CMOS N well process transistor and substrate contact construction. Substrate, gate, you have N transistor, P transistor, well connects, and these are the representations. Next we have metal rules. Metal spacing may vary with the width of the metal line. So single metal wires cannot be greater than a certain width. Nevertheless, width and spacing are still greater for thicker metal wires. Wire rolls, these are normally of uniform size within a layer. They may increase in size towards the top of the metal stack, and it has to be uniformly constructed. As I told, MOSFET, metal oxide semiconductor implementation system, is scalable CMOS rules. So this is in terms of lambda, very much common. I have already told you in the beginning. And MOSFET once offered a variety of processes from 2 micrometers. Normally it was 2 micrometers. Now it has been brought to 1.18. That is nothing but lambda value has been brought to 0.09, which happens to be 180 nanometers. So from micrometers it has been reduced to nanometers. Next we have micron design rules. So this shows the list of micron design for 65 nanometer process. So what exactly you say here, they are slightly different from the lambda based rules, where the lambda value is 0.03 0.035 micrometers, and these are the rules. So well is belonging to 1.1 rule, which says width should be of 0.5 micrometer. Similarly, well spacing to well is 0.7. So please go on to remember these different variables